Hi, I'm Bruce Momjian. Today I'll be delivering a talk called The Wonderful World of WAL. The write ahead log is a fundamental part of Postgres. It allows implementation of crash recovery, physical replication, and logical replication. People who are curious how these features work and how to make best use of them will find this talk entertaining and useful. Hello, let's dive into the wonderful world of WAL. This is one of my many presentations, and you can see my URL there is my homepage, which has this slide deck as well as many others. I'm going to be going through 6 sections today. We do have 103 slides, very exciting. First section, we'll talk about the write ahead log itself. It's a major feature of Postgres, which a lot of other features are built upon, but most people don't really study it as we are going to do today. Then we're going to go through various features that are built upon write ahead log, crash recovery, point in time recovery, physical replication, logic replication, and finally we'll talk about replication slots. Write ahead log is basically the change log for the database. It basically aggregates all the changes that you make in the relational Postgres database and puts them in one place. And believe it or not, that allows for a lot of amazing functionality to be built on top of that change log capability. And that's what we're going to be talking about today. Write-ahead log originally was developed in 2001. It was primarily done for crash recovery. Prior to that, Postgres did not have full crash recovery. There were some cases where you could have great corruption, for example, but that all ended in 2001 when we added the write-ahead log. 2005, we added point-in-time recovery. I'll be explaining what that is. It's basically the ability to have a continuous backup of Postgres. 2010, we added the ability to do streaming physical replication that allowed you to create replicas either for high availability or for load balancing. 2014, we added something called replication slots. And finally, in 2017, we added logical replication. And I'll be talking later about logical replication, how it works, and the very flexible data layouts that it allows you to set up. This is the normal flow of Postgres. You may have seen this slide before in other presentations of mine, but I want to just go over it a little bit. On the right hand side is the write ahead log. And what you can see there is that we have three backends at the top, the three purples. And every time they write to the shared buffer cache, in this case in red, they issue a write to the write ahead log. So you can see these three red arrows at the top, and they're all writing to a place called the WAL buffers. And the WAL buffers at the end of every transaction are F-synced not only to the kernel, but also to some type of durable storage. That could be a RAID controller, could be an SSD, could be a magnetic disk drive, but some place where the data is permanent, because as you may remember, relational systems much follow the ACID properties, and the D in ACID represents durability. So effectively, that's what happens with the write ahead log. We are flushing that on every commit by default. You can't change it, but by default, we are flushing that to durable storage. And again, that write ahead log is a list of changes that we've made to the database, and it aggregates them all together. To better illustrate what is inside the write ahead log, we're going to use something called wall inspect. In fact, anything in red on the slides is typically where you want to look because that's sort of the most important part of the deck. Also, if you want to run through this presentation yourself, you can see their URL there. You can actually download the SQL that you're seeing and run it yourself. This is a helper function I'm going to use, basically just to relabel some of the internals of the write ahead log. And this is a query I'm going to use, a common table expression query, which is going to call a function called pg get wall records info, which is going to dump the contents of the write ahead log. So if I install Postgres from scratch, so I run initdb, this is the type of write ahead log records that are generated. On the left, you can see we have resource managers on a different type of resources that are contained in the write ahead log. the number of records for each resource manager, the percentage of records, and also the percentage of size. And so it's just sort of a general layout. If we then run and look at a specific record type, we can see, for example, that the B tree resource manager has, in this case, it looks like eight different record types, which you can see the different things you do with a B tree: delete, insert a leaf page, insert an upper page, a new root, split a page, and so forth. And those are typical things you'd see in the write ahead log. When you do their database resource manager, these are basically things we would do for a new database. The heaped tables, which are basically the data storage tables, you can see things like a delete, a hot update, an insert, are all record types that we would have. Heap two, again, other types of heap records. PG wall is the write ahead log records, things like a checkpoint, full page image, which is FPI. We do have those indicated here. Zeroing a page for the transaction status file, that's PG exact. When you do a relation map, there's an update type there. For standbys, there are queries, record types, or storage for creating things. This is the record type when you commit a transaction. This is a record type that appears in the write ahead log. Now, if we go and we actually issue some commands, we're going to look at the write ahead log that's generated by certain command types. So a create table in this case is going to run this query, and it's going to generate these record types. So a create table is going to insert into B tree. We have a B tree resource manager. We have two heap records. We have two heap two records, and so forth. And a commit at the bottom. Kind of what do we expect? If we do an insert, we actually have again the same query, and we can see we are inserting into a B tree. We're inserting our new row into the heap, and then in a commit, which is exactly what we'd expect. If we do an update, we have an insert into the B tree, and we have an update to the heap, which we expect, and a commit. Kind of cool. If we do a delete, we have a delete and a commit. Pretty much what we expect. If we do a drop table, we delete the heap and we do a lock and we basically prune the heap because I think there's no rows in it. If we then insert a second row into the same table, we then have similar records, a little different. Okay. And if we then go to detail, we can actually see this is what the heap insert record looks like. Up top, you have logical sequence numbers and so forth. Um, and here's the second record type for an insert, the third record type for an insert. So I'm going through for each of the record types. And if I go to look at block info, I actually see a lot more detail. And in fact, down here in pink or magenta, the 0002 is there because you may remember we inserted 2, the value 2, and that's what that 0002 is, literally an integer, a 4-byte integer of a 2 inserted into that row. So what we're seeing here is effectively the data that I'm inserting is literally in the write ahead log. Okay. Um, we turn on logical replication. We have a little different, we have another type of record, which is a full page image. That's something we would do for the write ahead log, I'm sorry, for a logical replication. If we do an unlog table, now an unlog table, we do not actually log anything because it's not crash safe. It gets truncated on crash. It doesn't get replicated. So if we alter the table to be unlogged and we do an insert and we then go ask, give me the records that match the insert I just did, there are none because it's unlogged now. So we turned off logging for that table. So good illustration, I think, of that. So let's dive into the features built on top of the write ahead log. As I mentioned before, crash recovery was the first big feature that we designed on top of here. And that's exactly what we see here. Same layout you've seen before, right? The F syncs and so forth. And the way the write ahead log works for crash recovery is that we have the normal operation and we are writing and F syncing every time a commit happens to durable storage, which is the wall there, right? Now, what happens in a crash? Well, in a crash, we have heap and index files which were being written to potentially during the crash. So they may be inaccurate, they may be partial. So how do you recover a consistent database, not losing any transactions when you have heap and index files that potentially are changed? And the way we do that is that fact that we've f-synced all of those write-ahead log changes. We can actually replay on crash recovery. When we start up after a crash, the first thing the system does is it checks the write-ahead log. Was there a clean shutdown? If there was not a clean shutdown, the system starts a special Postgres worker. You can see it at the top right, and the Postgres worker will read the write-ahead log and effectively replay the transactions that may have been partially written to the heap and index files or not even written at all potentially to the heap and index files. They were written to the write-ahead log. So therefore, we're replaying them, okay? And as we replay them, the corruption and the missing transaction, the heap and index files, gets less and less until the system is now consistent and we've replayed all of the committed transactions that happened before the crash, which is great. And then as soon as that happens, we can just start up again just like normal and start writing the write ahead log again. Okay. So it's kind of cool. It basically, the write ahead log, because it contains a durable copy of all the changes, is allowing us to not only fix any corruption we have in the heap and index files, but also allows to recover any missing data that may have been in the shared buffer cache, but we didn't get a chance to write them to the heap index files at all, maybe before the crash. And this is what gives Postgres its durability. Okay. So let's walk through kind of what this looks like at the SQL level. And I'm just going to use grep a little bit to show you. And again, let's highlight the stuff in red. So at the top, I create a table and I insert a string called Postgres is awesome, whatever. Okay. Now, if I go to the data directory and I do a recursive grep on the data directory looking for Postgres is awesome, what's really interesting is I only see that string in the write ahead log. Where I don't see it is in any of the heap and index files at all. Because again, durability requires us to write to the wall on commit. It doesn't require us to write to the heap and index files because we have this crash recovery to fix it. So then I actually wait for a checkpoint timeout. Checkpoint is effectively a flushing of all the shared buffers down to disk. I'll talk about that in a minute. And once I wait, I now see at the bottom that in red, I have still the entry in the write ahead log, but now in blue, I have the Postgres is awesome string also appears in one of the data files. So this kind of shows you the delay that can happen between actually committing a transaction that adds a string and then actually writing it to the heap and index files. This is what a checkpoint looks like. It effectively on the left, it finds all of the dirty buffers here indicated by 1. And during the checkpoint, it writes all of those to durable storage to the heap and index file. And once it writes to heap and index files, then it can effectively recycle the write ahead log. Because once we've written the write ahead, the dirty the dirty shared buffer pages, we don't need the write ahead log anymore because we now know that all the data is now durably stored. And that's why the write ahead log doesn't grow unbounded. It effectively is continually recycling these files. If we let's go and simulate a crash. So here I've insert into a new string, long live relational systems. Okay. And then I grep for that, and I can see it's only in the write ahead log in red. At the top, you can see that. So now I issue a PGCTL immediate stop, which effectively simulates a crash of Postgres. And when I go to grep again, I still only see this string in the write ahead log. I don't see it in any data files. Okay. Now, when I start Postgres, it's going to go through crash recovery. All this data in red, all the strings in red indicate it's going through crash recovery. It's reading the write ahead log. And then at the bottom in blue, it says checkpoint complete. And that means it's finished basically replaying the write ahead log and then issuing a checkpoint, making sure everything is stored to the data files. And now, if I do a grep again, you can see that long live relational systems, yes, it still appears in the write ahead log, But above that in red, you can see that it does appear in one of the heap and index files. And that is only because of crash recovery. And now when I do a select here at the bottom from the table, I can see Postgres is awesome and long live relational systems. That long live relational systems was we remember we inserted that right before we crashed the system. Yet once we started up, it properly restored it. Okay, so that's crash recovery for write ahead log. Now we're going to talk about continuous archiving. As I said before, continuous archiving is basically a way of sort of continually backing up your system. And I'm going to explain the mechanics of this, but it's incredibly useful because obviously having a backup at a point in time is useful, but having a backup that is continuous that could restore to any point in time, including up to the failure point, is much, much more valuable. So what we have here, the standard diagram on the left, but also on the right, we have a wall archive. So that is the write ahead log archive, and it allows us to store huge amounts of write ahead log files as they're generated off into another location. Okay. So how do we actually set up continuous archiving? What we do is we do a file system backup of the heap and index files, which is kind of interesting. And this is done while Postgres is running. So as you can see at the top right, the backup we do of the heap and index files is in some way corrupt because we're writing to it as we're backing it up. So who knows what state it's in. But the part underneath that is that we also back up the write ahead log that was generated during the backup. Just like crash recovery allows us to recover from a crash, this this facility here, continuous archiving, allows us to recover a corrupt backup, even though the system's running, because we have the wall, which we can replay and fix any of that corruption. Okay. So the way this normally works is that Postgres, you want to do recovery. So you take the part in the upper right and you restore it. So now I have a new server with a effectively corrupt heap and index because those files were modified as the backup was going. But I do have the matching write ahead log back for during the backup. So now when I start Postgres, what happens is that I just like during crash recovery, I read the write ahead log that's matching the backup. I replay that just like I would during crash recovery over to the heap and index files, and it gets less corrupt, less corrupt. And then now, once I've replayed all of the write ahead log that was during the backup, I can now start to pull files from the write ahead log archive, which is on the bottom right, and then basically pass those and then replay those, which allows me to go past the time of the backup all the way forward until the point where I want to recover to. Okay. So that's a success. Now I've got a successful recovery, and now I can start up Postgres and run it just like before. And again, it's now running with on my recovery, my point in time recovery. Let's look at the SQL behind this. So now I'm going to run as Postgres. I'm going to create an archive directory. I'm going to turn archive mode on. I'm going to issue an archive command. And effectively, what I'm going to do is I'm going to look at the archive directory. Currently, there's nothing in it. But in blue, if I switch the write ahead log, so PG switch wall, as soon as I issue that command, it's going to create a new wall file. And as soon as I create a new wall file, the old wall file, which ends in 001, is automatically going to be completed and then archived into that archive directory, which is what I expected. I'm going to run some tests. So now I'm going to insert a string called pre-wall switch message in magenta. Okay. And you'll notice that that is only in the write ahead log. It's not in the archive directory. If I then issue the PG wall switch, you now see that that pre-wall switch message now appears in the archive directory as well as the write ahead log. That's exactly what we expect because it was in the wall. We'd said the wall was done, so we automatically moved it over. Okay. Now, if I issue a pre-backup message and I perform a base backup, you can see the pre-backup message appears in the archive directory, which is great. It also appears in the heap files. I'm going to now issue a post backup message. I'm going to switch wall again. and you're going to see that that's also now in the archive directory. And now I'm going to do point in time recovery. So I'm going to restore point in time recovery. I'm going to stop the server. I'm going to delete it. I'm going to restore my backup. And then down at the bottom, you can see that the system was able to restore the message that was done before the wall switch, before the base backup, and even the one after the base backup. And this is what you want to see. Okay. Continue archive is still running, but again, it now I'm running forward and I'm actually running with a new timeline. So this 2 here that you're seeing in red indicates I'm now have new wall files because I've done a point in time recovery. I'm now using a new timeline, which is number 2. And you can see now we have mixed ones and twos in the archive. Okay, let's talk about physical replication. Physical replication is a little different than point in time recovery, but not a whole lot. You do a base backup just like before. Okay, top right. But then instead of restoring it in the same location, we store it on a different server. Okay, and then we start up Postgres on that new server, and the same process occurs. We then read the write ahead log that was generated during backup. And we, again, you can see on the right, it's reducing the corruption. And now, once we've recovered it, we can pull files from the write ahead log archive, but we now also have a network connection, which is giving us a stream of changes that is now going to the physical replica. Okay. This is how you set it up. We set up a connection info between the 2 servers. And now you can see when I create a table on the replica, on the primary, it automatically gets created on the replica. If I do an insert, the insert appears in the replica. If I do an update, the update appears in the replica. And if I do a drop, the table no longer appears on the replica. And that's exactly what you have in physical replication, identical servers. And you can do hierarchies of servers where different replicas feed other replicas and so forth. Very fancy. Let's talk about logical replication. This is a much more fine-tuned way of doing replication. Instead of doing the whole cluster, you're doing individual tables. So here we basically have a schema that we then create an empty table on the replica, and then we create a publication on the primary, and we create a subscriber on the replica. And then we effectively, once we create that publisher subscriber link, we have a copy command is issued on the primary and it sends all the data to the replica. And then once we've copied that data, we start streaming changes for just that table over from the primary to the replica. So this is the way you set it up. We do a base backup, for example. We set our record level to logical. And now you can see on the primary, we create a table, we create a publication, and then on the replica, we create a table, create a subscription. And now you can see that the inserts match and the updates match because we now have linkage between the 2. You can set up all sorts of very interesting architectures with logic replication, much more flexible than physical replication. You can do something like a broadcast where you have a publisher sending to multiple subscribers. You can have multiple publishers sending to one subscriber. This is what we call an aggregate of all your data in one place, maybe for data warehousing. You can do bidirectional. One table goes one way, one table goes another way. You can do partitions where one partition goes one way, one partition goes the other way. You can even do odd and even rows if you want to. And one thing people really like about logical replication is the ability to do major version upgrades because you cannot do major version upgrades easily with physical replication. With logical, you certainly can. Okay. Just to finish, one concept I wanted to introduce, and you might be thinking about this. How do you make sure I mentioned earlier the write ahead log gets recycled? How do you make sure the write ahead log doesn't get recycled when it's needed? And that's basically provided by something called replication slots. And this is the checkpoint process. Remember, I showed you how we recycle the write ahead logs, but effectively and this is the way that the streaming works. But effectively, what replication slots are is they're basically pointers into the write ahead log, and they allow you to reserve write ahead log space so it doesn't automatically get recycled for you. So these replication slots effectively retain wall long enough for the replicas to get their data. And as soon as they've gotten their data, we advance the replication slot. And of course, the oldest replication slot is where our limit is of how much WAL we can recycle. So that might have been something you thought about, and that's why I wanted to kind of bring that up. We have a function that allows you to list all the replication slots. Um, it's particularly useful for logical replication where you have things maybe disconnecting and connecting all the time. And you can even run this query and it shows you even subscribers that are part of the replication slot. So I want to thank you today. I really always wanted to talk about the write ahead log, and there's just so much around this feature now that's built on top of it, that it's a foundational part of Postgres and one of the things that makes Postgres such a great database today. Thank you for listening to me.